Hi. In the last video we talked about how work can change the energy of a system. In this video I want to actually quantify work. I want to come up with an expression for work so that way we can calculate how much work the environment is actually doing on a system. So I want to consider a hypothetical situation for the next couple videos. And that hypothetical situation is that imagine pushing a block, right, as it moves along a frictionless track. I'm not telling you how I'm pushing the block, in which direction. I'm just simply saying that I'm pushing on this block as it's already moving along a frictionless track. So I'm applying a force, right? I can think of, if we look at a top-down view of this track, and I have this object, and I'm going to apply some sort of force to it. This is going to be our environmental force on our system of the block. I can think about that force, right, as some force in a direction. I'm going to use that general directional variable called S that we used a lot in chapter 1 and 2. Basically because I don't know if it's going to be in X, I don't know if it's going to be in Y, I don't know if it's going to be in Z. I'm just simply saying that it's going to be in a direction, and that direction is going to be S, to be just nice and general. So I have this force, right? I'm going to have that equal to MA in some S direction. I can rewrite that a little bit by saying M, and I know that the acceleration of something is the derivative of the velocity in that direction, right, with respect to time. So I have m dv dt. Now I'm going to do a quick switcheroo. I'm going to do a little bit of a mathematical trick here. I'm going to use the chain rule. Right? The chain rule in calculus allows me to say that, well, dv dt is equal to dv ds times ds dt. Right? Mathematicians don't really like when we kind of say this, but the DS's kind of cancel out, and I'm still left with dv dt, right? That's not really the best way to approach derivatives, but we can kind of squint and see that happening here. So, but the ds dt, that's something that we're also familiar with. It's our velocity, right? It's our change in position versus time. And so what I've really done is say that dv dt is equal to v in a certain direction times dv ds, right? And dv ds is how much does that that velocity change per direction, right? Per length change, per distance traveled. So if I kind of if I throw this in to my equation here, I can say that my force in a certain direction is equal to m times v times dv ds. Let's just make sure that we're explicit. The v is in a certain direction. It's in the s direction. So I think everyone's probably seeing where we're going with this. We need to take an integral here, right? I'm going to integrate fs. I'm going to throw ds on the other side, right? Equals the integral of m vs dvs. And this turns into the integral from s1 to s2 of fs ds. That's equal to 1/2 m vs squared when evaluated at vs1 and vs2. Now, hopefully that right-hand side looks a little familiar if you've taken physics before. it should ring a bell. This is what we're going to call kinetic energy. So I can kind of simplify this a little bit further. I can actually define this term on the left, the integral from S1 to S2 of Fs ds, as the work done on a system. And that is equal to, right, that's equal to this change, right? Let's write out one more step. I'm going to say 1/2 mvs2 squared minus 1/2 mvs1 squared. Another way of kind of shorthand writing this is it's the change in 1/2 mv squared, right, when evaluated at two different locations. So this, right, this stuff in here is what we're going to call kinetic energy. And it's a measure of how much a system is moving. But not only just how much it's moving, but how much mass there is involved in it. It's a scalar quantity. Notice that there's no direction associated with it, even though we have velocity in it. Because we're squaring the velocity, we actually get rid of any of that directional information. And so our work is equal to the change in kinetic energy. Maybe that's another way of writing this. And this is sometimes called the work kinetic energy theorem, that any change in work from the external forces is equal to the change in kinetic energy of a system. Now, if we're thinking about units here, right, I have some integral of f and a distance, so I'm going to think, right, Newton meter, right? If I think about kinetic energy, that's going to give me what, kilograms meters squared per second squared. These are actually equal to each other. They have to be, right? But they're equal to each other. And what we're going to call these two ways of writing the same thing, we're going to give it a name for this unit of energy. And we're going to call it a joule, right? A joule. So a joule is our basic energy unit. We're going to simplify it with an uppercase J. For our class, this is our base unit of energy. And so a joule per meter is going to be a Newton. And kilogram meter squared per second squared is going to be a joule. So all in all, we have delta K is equal to the work done from an external force. Next time, we're going to actually talk about how to maybe write this a little bit better, about the force, different ways of simplifying this force integral, and what assumptions we can actually make there. We're going to also revisit our old friend, which we mentioned in Chapter 3, but it was never actually brought up again until now, the dot product. So I'll see you next time. Thank you very much for watching.